All right, chemistry class, we are going to continue our discussion about solutions in this next chapter, chapter 13. You'll notice here that we are going to talk some more about solutions, and particularly when you put an ionic compound in, for example, a solvent like water, creating those ions. We talked about that before. We're just going to expand on it a little bit and continue that discussion. All right. In your notes, put down section 13.1, and we're going to talk about compounds in aqueous solutions. Aqueous obviously means it is in water. Okay? Now, when we put certain compounds in water, aqueous solutions, we're going to be talking about ionic compounds and molecular compounds, or we sometimes refer to them as being covalent. Covalently bonded. So remember, ionic compounds, this is a metal and a nonmetal, metal and a nonmetal, and then covalent are usually all nonmetals bonded together. Alright? Ionic is when there's a transfer of electrons. Covalent is when they're sharing those valence electrons, those outer electrons. Okay? We're just going to look at the difference between these two types of compounds and what happens when you put them in water. All right. First thing you need to know, put down point A here, ions, so this would be coming from an ionic compound, ions separate from each other. They're going to separate. An ionic compound is a metal and a nonmetal, and the metal likes to give up its electrons to the nonmetal, creating charged particles, ions, and then those oppositely charged particles are attracted to each other. Well, when you put them in water, those ions break apart, as I'll show you. So the dissolving process for an ionic compound results in that compound breaking apart into its ions. That process is called dissociation. Associate means you come together, dissociate means you are spreading out, you're breaking apart. Okay? So dissociation is the separation of ions when an ionic compound dissolves. So here, for example, here is a flask that has water, and you put in salt, table salt, sodium chloride, and you'll notice that when you put it into the water, the sodium ion and the chloride ion are now separated, and they are in the solution as separate ions. A positive sodium metal cation and a negative nonmetal chloride ion. That is an anion, negative. Okay? And you'll notice that they are surrounded by water. Each of them are surrounded by the water molecules here as it gets hydrated, as the solid becomes hydrated. So here is a kind of you could write this as a chemical equation. It's not really a chemical reaction, but we could write this as an equation here showing sodium chloride, solid, that's what the S means, remember, and when you draw your yield arrow here, yields, and you put H2O above it, that means you're going to add it to water, you're putting it in water. What results is you have a sodium ion and a chloride ion. Now, of course, this is in water, so you would have water as well, but that is just assumed. You're assuming that this is going in water, and you know water molecules are in the solution, but you are focusing on the ions that are created. So you have to balance this, since this is 1 unit of sodium chloride, and it breaks apart into 1 unit of sodium and 1 unit of chloride ion. Okay, 1 sodium ion, 1 chloride ion for every one unit of the compound. All right. Now, dissociation specifically refers to when an ionic compound dissolves. If a molecular compound is dissolving, we just say it's dissolving, but not dissociating. It's not breaking apart the molecule. Each individual molecule is being surrounded by water when a molecular compound is dissolved, but it doesn't break apart like an ionic compound does. Okay? So here, for example, if you have sugar, let's say this is a cube of sugar right here. All right, you got a cube of sugar, and you introduce water to it. Well, that water is going to get in and start to pull apart the individual sugar molecules. Water is polar. The sugar molecule is going to get, the water is going to get in there and be attracted to the sugar molecule. And notice here, the water is going to surround the sugar molecule, surround the sugar molecule, surround this one, and break them apart into individual sugar molecules. That right there is a sugar molecule. But the molecule does not pull apart. The sugar molecule is still intact, but you're just separating the individual sugar molecules, so much so that when you put sugar into water, it dissolves so well that it appears clear, and you really can't tell whether it's sugar water or just plain water. Okay? What happens when you have an ionic? This one appears molecular, like sugar, covalent we say sometimes. It's covalently bonded. Here, this is ionic. With an ionic compound, what happens, let's take sodium chloride, and you put that into water, it breaks apart into its ions. The sodium cation and the chloride anion. It breaks apart into ions. What actually happens is, here's your water molecule, your H2O, and it gets in there and is attracted to the positive sodium ions and the negative chloride ions because water is polar. It has a negative partial charge on the oxygen side, and it has a positive partial charge on the hydrogen side because the electrons spend more time on the oxygen side, even though it's a neutral compound. So water gets in here and is attracted, and notice here is your sodium, your positive sodium ion, and it is the negative end of the water molecule that is surrounding it and attracted to it so that the sodium is pulled away from everything else. And here's your chloride ion, it's negative. Well, now it's the positive end of the water that is attracted to the chloride negative ion, and it's going to pull those all apart and separate them and surround them. So each ion is going to be surrounded by water, but in the sodium positive ion case, the water is surrounded, and it is the negative part of the water molecule that is pointing toward it. Down here, with the chloride ion, it is the positive part, positive side of the water molecule that is attracted to the chloride negative ion. Okay? So, as I said, we can write this as an equation. So you have sodium chloride, solid, you have 1 mole of that, just look at the coefficients here, is going to be hydrated and produce a mole of sodium ions and a mole of chloride ions. And we can balance this. It's already balanced, but if it isn't, we would have to balance it. Okay? So we can show the moles of the dissolved ions this way. Here's another one. Let's practice one here. Here we have calcium chloride. Now just realize the formula for calcium chloride is CaCl2. Why? Because calcium is in column 2, so it wants to give up 2 valence electrons. It has 2 outer valence electrons. So when it does, it's going to become a 2 plus. The chloride is going to need 2 chlorides to accept those 2 valence electrons from the calcium. So you need 2 of these because chloride only wants 1. Each of them wants 1. Chlorine wants just 1 more electron to complete its outer shell. So the 2 chloride valence electrons are going to be donated 1 to each of the chlorine atoms to make them ions. The calcium becomes a 2 plus ion, the chlorides become a -1 each because they each gained an electron, and you're going to have 1 calcium ion attracted to 2 chloride ions to make a neutral compound. Okay? So when this breaks apart, this is going to break apart into calcium, 2 plus, and now these 2 calciums are going to get freed up, each of them surrounded by water molecules, and you're going to have 2 of these, 2 chloride ions. Not just 1, here they are, they're right there. There are 2 in that formula, So they're both going to be separated and pulled apart. So when you see a subscript here in the formula, realize you've got to put a 2 in front of that particular ion. They're not bonded anymore. They're separated. That's why I'm putting a 2 in front. This coefficient is telling me how many I have. So this could say 1 mole of calcium chloride is going to hydrate or dissociate when it's put into water into 1 mole of calcium ions and 2 moles of chloride ions. You have to respect the formula. In here is a calcium ion for every 2 chloride ions. So after you hydrate it, you have to show there's 1 calcium ion for every 2 chloride ions. Okay? When it's in a formula and bonded, the 2 is a subscript. But when they're not bonded, the 2 is out in front as a coefficient, showing you that there are 2 separate chloride ions. Okay? All right, let's talk a little bit about when there's a precipitate that is formed. Okay? We are talking about ionic compounds right now, but now let's talk a little bit about what happens when you have a precipitate that is formed. And I'll show you what that is. Now, ionic compounds are going to dissolve to a different extent. Some of them dissolve very well, others don't dissolve well at all. So they're going to be soluble, meaning they dissolve to some degree, some very well, some very poorly. Okay? Sodium chloride, for example, is very soluble. But then there are others that are not very soluble. Okay? They would have a low solubility. In fact, what we say is that they are insoluble if they don't dissolve very well. All right? So if I look at these 6 test tubes right here, they all have water in them, or had water in them originally, and then a solid was added. And here are the solids that were added. Here we have nickel 2 chloride was added to test tube A. We've got potassium manganate and copper sulfate, copper 2 sulfate, lead 2 nitrate, silver chloride, and cadmium sulfide, I believe. All right? And if you analyze these, you'll notice that there are 2 of them that have a solid at the bottom. These 2 right here. All the others look like the solid dissolved pretty well. There might be a color change because it says here nickel chloride actually forms a green solution. It turns it green. Okay, this is going to be green here. And then the potassium manganate forms a purple solution just because of the color of the ions that are in there. But all of them dissolved, or I should say dissociate, except these last 2. So that tells us that silver chloride and cadmium sulfide are not very soluble. We might even say they're insoluble. All right? So you cannot write solubility equations or formulas for these particular 2 solids. They don't dissociate. You can't write an equation for those. We could for the other 4. For example, nickel chloride here, nickel 2 chloride, is going to dissociate into nickel and chloride ions. Now, how do I know what the charges are? Well, you have to know a little bit about when we talked about the ions. Chlorine always forms a -1 ion. It's always a -1. And if there are 2 of them, there are 2 there, then nickel must be a +2, because remember the charges all have to add up to 0. So nickel must be a +2, each chloride is a -1, and there are 2 of them, and this is how you would write the dissociation equation for nickel chloride. Here, this is potassium, and then this guy, MnO4, is a polyatomic ion, manganate. And notice, potassium, you would have to know that is in the first column, so it's always going to form a +1 charge ion, and then that must mean this polyatomic ion, manganate, forms a -1. The whole thing is a -1. Okay? This is copper sulfate. If you look at this polyatomic ion, sulfate is always a -2. You can look at the chart for that. Copper, therefore, must be a positive 2 because there's just one copper for every one sulfate. And that's how that would dissociate. Here we've got lead, nitrate. And if you look on the table, nitrate is a -1. And there are 2 of them. So I have to put a 2 in front of that. It's a -1. So this is 2 negatives, 2 -1 polyatomic ions. So that means the lead, since there's only one lead, must be a +2 in order to have a combination that eventually would be 0 for the molecule. And then these two don't dissociate. They just stay as a solid. They don't break apart. Water, the bond between silver and chloride here is probably too strong for the water to get in there and pull it apart. Same thing with the CD and S, the cadmium and the sulfur. Too strong, the water can't get in there and remove them, separate them into their ions. Okay. Now, there are some guidelines that tell us what is soluble, which ionic compounds are soluble. So there's a whole table of solubility guidelines. You don't need to memorize it. You'll always have it available to you to refer to. But let's just talk about them really quickly here. Notice it says sodium, potassium, and ammonium compounds are always soluble. Anything that has sodium in it, potassium in it, and ammonium in it, if you see those particular elements or polyatomic ions in the compound, you know it's soluble. So sodium chloride, potassium chloride, ammonium chloride, those are always going to be soluble. Number 2 says anything that has nitrate in it. Nitrate is NO3. Acetate, you can look for the formula for acetate. And chlorates, you can look that up as well. Anything that ends in, these are polyatomic ions that would end the ionic compound. So sodium nitrate, sodium acetate, sodium chlorate. Anything that ends in nitrate, acetate, or chlorate would be soluble. Anything that ends in chloride, sodium chloride, magnesium chloride, anything that is chloride are soluble except for silver chloride, mercury chloride, and lead chloride. Okay? And then number 4 here says sulfates are soluble, but there are some exceptions. Barium sulfate, strontium sulfate, lead, calcium, and mercury sulfate are not soluble. All the other metals that would combine with sulfate would be soluble. Carbonates, phosphates, silicates are insoluble. Now we're getting to some that are insoluble. So if you see anything that ends in carbonate, CO3, phosphate, I think that is PO4 maybe, okay? So if it ends in those, so sodium carbonate, although sodium would be soluble, okay? But anything that ends in a carbonate there is most likely going to be insoluble, except for, as I said, sodium, potassium, and ammonium, because that is rule 1 up there, okay? And then anything that ends in sulfide, that's S. Anything that ends something S. So magnesium sulfide, for example, are insoluble. All right, except calcium, strontium, sodium, potassium, and ammonium, because that's referring back up to rule 1. So again, that's just an overview. You don't need to memorize it because you can just refer to it. If you want to know if something is soluble, just refer to this table and see if it has any of those particular elements or polyatomic ions in it, and then you'll know. Okay? The reason why we have that guideline is the solubility guidelines listed above are important to determine what happens when 2 different soluble compounds are mixed. Okay? So we're going to determine what happens if in a reaction the potential is for something, one of these to be formed. What if something like this is to be formed? What if we're going to form a something that has sulfide in it? If we're going to form something that has sulfide in it, then we know that particular compound probably is going to be a solid, and it's going to precipitate out. Okay, and we'll see that in a little bit. So here, for example, there is a solution here In the beaker, we've got a solution that has cadmium nitrate in it. And this solution in the test tube is ammonium sulfide. Both of these are soluble. Okay? These are soluble. Ammonium, that was rule 1. This is soluble, has ammonium in it. And here, nitrate, this is soluble, has nitrate in it, soluble. But now we're going to mix them together. We're going to pour the ammonium sulfide into the solution that has the cadmium nitrate. What happens? Well, remember, in solution, these ions are free. So here's the sulfide ion surrounded by water. Here's the ammonium ion surrounded by water. Okay. Down here, here's the cadmium ion surrounded by water. Here's the nitrate ion surrounded by water. They're free. They're not holding hands anymore in the solution. They're free. And now when you mix them all 4 of these ions are going to be able to interact. Okay? That means if they bump into each other and form a compound that does not dissolve in water, it is going to form a solid. So here's what happens. Ammonium from this solution, solution number 1 up here, could bump into nitrate from solution number 2, but ammonium nitrate is still soluble. They're not going to form a bond and form a solid because they're going to just stay as ions and stay surrounded by water because it's soluble. But if the cadmium from here, from solution number 2, and the sulfur from solution number 1, if they bump into each other, they're going to form a bond that water's not going to be able to get in and separate. And they're going to form a solid right here. This is the solid that's being formed. Okay? So after the reaction, what you have is you've got this cadmium from solution number 2, here it is, and the sulfur from solution number 1, there it is. They bump into each other and they form a solid, and that is this cloudy precipitate that you see right there. And then the ammonium and the nitrate, they're still aqueous, meaning they're still dissolved in water. We show them together, but really, it really is CDS. There's your solid. And then also in the solution, you've got the ammonium ion, AQ, and you've got the nitrate ion, AQ. They're still separated. They don't come together and form a compound, a solid. They stay hydrated in the solution. But this cadmium sulfide right here, they come together, they hold on to each other so strongly that water can't separate them, and as a result, you see the solid as a precipitate. Okay? So this is here, this is in solution number 1. This is the ammonium sulfide. They break apart into ions. Here's solution number 2, cadmium nitrate. Okay? And when we mix them, now we put all 4 of these together, well, we combine all of them together in one. It is the ammonium and the nitrate. They're not going to form that precipitate. This is just going to be dissolved in water. But this cadmium sulfate, if you look back up at the table, you'll note, or sulfide I should say, sulfides are insoluble. So cadmium sulfide is going to be insoluble. This is going to be your solid right there. Okay? The other potential compound is actually no compound at all because it's still aqueous, it's still dissolved. Or I should say dissociated. Okay? But this is your dissociated. Sorry about that. Dissociated. Dissociated. Yes, something like that. Okay. Here we've got our solid. This is your precipitate. Okay? This is your precipitate. All right. All right, let's talk a little bit about what are called net ionic equations. Basically, we've already showed that we can write equations when you have a dissociation of an ionic compound. It breaks apart into ions. Well, let's just take this a little bit further here, okay? An equation, you can write this down, an equation that represents aqueous solutions, remember that's water, aqueous means it's dissolved in water, of an ionic compound, that's a metal and a nonmetal, as ions, we're going to represent it as ions, that's called an ionic equation. Okay? And then the net ionic equation is showing everything that is producing a mostly the solid. Okay, so here's what I'm saying. Look here, chemical reactions. It includes only those compounds and ions that are going to have a chemical change that in this case are going to produce the solid or the precipitate. Okay. And then there's something called spectator ions, and those are basically the same before and after. Now all of that seems confusing, but let me show you an example and it'll make sense. Okay? Alright, here we have, this is the same equation from our previous example. Remember, in one solution we had ammonium sulfide. That was in one solution. We took the solid ammonium sulfide and we put that into water, and that broke apart into these two ions right there. That's from one solution. And then in the other solution we took the cadmium nitrate, put that into a solution to water, and it broke apart into ions, creating these two ions right there. Then we mix them together. See the plus sign right there. We mix these two solutions together. We put them in the same container, the same solution, and now all four of these ions can interact. All four of them can interact. Well, if you have to have a, this is a cation joining with an anion. That's what this is right here. It's a cation and an anion that made up the ammonium sulfide, a cation and an anion that made up the cadmium nitrate. But now we can have a different combination. We can have the ammonium and the nitrate, because they're in the same container now, and we could have the cadmium and the sulfide. Those could get together. All right. If ammonium bumps into nitrate ions, ammonium nitrate, this potentially could be formed right here, ammonium nitrate. But this is soluble. This is soluble. This still dissolves in water. So even if they bump into each other, they're not going to have a strong enough attraction to overcome the water that's surrounding them. And this is still going to remain as ions. Okay? So the ammonium and the nitrate ions will still remain in solution, dissolved, or I should say dissociated. But when cadmium and sulfide, when these two ions collide, they form something that is insoluble. It does not stay dissolved in water. The attraction is stronger there, and so they come together, and as a result, the water can't pull them apart. And now you do see that chemical compound. You see that solid in the solution. Okay? So you'll notice that this here is our ionic equation. It's showing the ions. This is our ionic equation. Okay? Now, the spectator ions, as I mentioned up here, those are the ones that are the same before and after. Ammonium was an ion before, it's still an ion after. And the nitrate is before and after, it's exactly the same. So if we cross those out as is shown here, we're crossing out the spectator ions, we end up with just the sulfide ion from solution 1 and the cadmium ion from solution 2. Solutions were mixed together. Now they can get together, the sulfide and the cadmium, and as a result, they are the two ions. Remember, this sulfide was from solution 1, the cadmium was from solution 2. They are the two ions that are resulting in the solid, the insoluble cadmium sulfide that is our precipitate. After you cross out the spectator ions, you now have what is called the net ionic equation, only showing the ions that are actually changing or part of the chemical reaction producing this solid here. Okay, so it's a process You write the ions from each of the two solutions, and then you determine which combination, if any, is going to give you a solid. It's insoluble. You have to refer to the table, the solubility table, and you cross out the ones that don't change, that are still dissociated in the aqueous solution. And then you just write what remains, showing which two ions came together to produce that solid. Okay? All right, a molecular compound ionizes in a polar solvent. Let's see what that means exactly, okay? An ionic compound forms ions in solution through the process called dissociation. We've already talked about that. Ions break apart. Ionic compounds break apart into their ions, okay? Molecular compounds can also form ions in solution. Let's see how this works. However, molecular compounds undergo a different process. Ions are formed from solute molecules by the action of the solvent in the process called ionization. Now, that may seem confusing, that ionization happens when you have molecular compounds, which don't originally have ions in them, but let's see how this works, okay? Here we have HCl, hydrogen chloride, or when you put it into water, it becomes an acid, and we'll talk about acids and bases later on. Okay? Now this right here, this is a non-metal, hydrogen, and another non-metal, chlorine. So this is a molecular compound. It's a molecular compound. When we put it into water, it actually breaks apart. Hydrogen often acts as a metal. So even though it's not a metal, remember it's in group 1 along with all those metals, and it often acts as a metal. It has one valence electron. If it can get rid of that one valence electron, it becomes a charged ion, charged particle right there, a cation. Chlorine is a nonmetal. It likes to gain that one electron to complete its outer shell, and so it'll do that from the hydrogen. So even though this is a molecular compound, often if it has hydrogen in it, it will act like a metal and will break apart into ions. Okay? And so you're going to have the H plus ion and the chloride ion. And we'll talk more about that as it results in an acid. Okay? What actually happens here is this H2O, an H2O molecule, attaches itself to the H plus. And what it really produces is an H plus, and H2O is an H3O plus. That is called the hydronium ion. That is a hydronium ion there, and then the chloride ion. Sometimes you won't see the H3O plus, but it's understood that this H plus in water is actually producing the hydronium ion. Okay? That's actually what is happening. Sometimes we just drop off the water and just write H plus and the Cl negative. Okay? So that hydronium ion is a result of this H plus in your original molecular compound combining with a water molecule. Again, creating ions. It is being ionized. Even though this is a covalently bonded or a molecular compound, ions are created because the water pulls them apart, and the hydrogen's acting like a metal here. All right. So here's what happens. Here's the HCl. Here's your model. All right. And here's the water. When you put HCl into water, this water is going to pull away the hydrogen from the Cl, and as a result, you get the H2O and the H combine into H3O plus. Notice the ion there. And then the Cl is left by itself to create its ion. And you are getting ions even though this was a molecular compound, not an ionic compound. Okay? All right, let's look at an example here. This is a great example. It's going to take us through several different steps. We have to be able to write the formulas from the names. We have to balance the equation, and then we have to break it apart into its ions, and then cancel out the spectator ions to get the net ionic equation. Lots of good stuff here because we are building upon what we already know, some previous information. Okay, so let's see what we have here. We want to write the reaction between zinc nitrate solution and ammonium sulfide. So we have to be able to write correctly those formulas. Zinc forms a 2+ ion. Nitrate, if you look on the polyatomic ion chart, nitrate is NO3 negative, so it's a -1 and a +2. So you're going to need two nitrates to combine with the one zinc. This is the formula for zinc nitrate right there. Ammonium, if you look on your polyatomic ion chart, ammonium is a +1. Sulfide is in the oxygen group. It forms a -2 ion. So you're going to need two ammonium to combine with the one sulfide. That's why it's NH4 2 and then S. There's the formula for ammonium sulfide. These are both in water already. They are dissolved in water. Okay? They're dissolved in water. So I'm actually going to skip down here and let's break these apart into their ions. So when you put the zinc nitrate into water, it breaks apart into the zinc ion and two nitrate ions. Why? Because you had two in the formula right here. There are two in that formula, so you're going to break them apart and have two separate nitrate ions. The ammonium sulfide is going to break apart into two, see this two right here? Two ammonium ions and a sulfide ion. So now all four ions you're going to mix together. You're going to combine the solutions. Combine these, here's the plus sign, you're going to combine both of these solutions into one. Alright? So what is the result of? Now, well, we know from the one solution that zinc and nitrate, when they combine, they stay dissolved, they stay dissociated. And the ammonium and the sulfide, they stay dissociated in their solutions. According to the solubility table, they just stay dissociated. They break apart into ions. But now that they're mixed together, now zinc could combine. You have to put a plus ion with a negative ion, with the other negative ion. What if zinc and sulfide got together? Well, if zinc and sulfide got together, they could potentially create zinc sulfide. Zn, this is a 2+, sulfide is a 2-, so just one of each of those to make that formula. Okay? And the ammonium, this plus this cation, could get with the other anion. This is a +1, this is a -1. So you only need NH4 and NH3. That's the formula there. Okay? If we balance this, we're going to have to put a 2 in front of the NH4, the ammonium nitrate, in order to balance it, because you need 2 ammonium and 2 nitrate. So we have to double this formula here to get the same of both sides. Okay? These are the new potential compounds. Okay? When we take the cation from solution 1 and combine it with the anion from solution 2, and the cation from solution 2 and combine it with the anion from solution 1. Now, we check our solubility table. Ammonium compounds are soluble. That's why it's AQ. This is still going to stay as ions. This is still going to stay separated. So the nitrate, 2 nitrates, 2 ammonium are still going to be dissociated in the new combined solution. But the zinc and the sulfide, if you look at the table, the solubility table, sulfides are insoluble. This is the one that when they get together, they form a solid, and the bond is stronger than what the water can pull them apart, and they are going to be the precipitate. So you'll notice that the nitrate was an ion before we mixed them, and it still is after. The ammonium is an ion before, and it still is after. It is the zinc from solution 1 and the sulfide from solution 2 that came together to give us the zinc sulfide. So we cross out all the spectator ions and we write only the ions. Again, this was from solution number 1, this was from solution number 2, that are forming our insoluble solid precipitate. Okay? Now we talked about electrolytes before. An electrolyte, basically, it depends on how many dissolved ions in there. An electrolyte is when you have ions in your solution, and those ions can conduct electricity. Remember, that's the test for an electrolyte. You basically have taken an ionic compound, or it could be you took like HCl from our example before. That creates ions as well. And you take that and dissolve it in water, and you're going to create those ions. Those ions are going to dissociate, and you're going to have a charged solution, if you will, that can conduct electricity. Now, electrolytes that conduct electricity very well are strong electrolytes. It just depends on how many ions it actually is produced. Okay, some are going to dissociate very well. Some dissociate just a little bit. Electrolytes that conduct electricity poorly are called weak electrolytes. That makes sense, right? All right. So just to take this a little bit further, a strong electrolyte basically all soluble ionic compounds are strong electrolytes. Okay? So if it's an ionic compound, and if it's going to dissociate in water, they're pretty strong electrolytes. They dissociate pretty well and are going to conduct electricity. Okay? Weak electrolytes are usually going to be some molecular compound. Remember I told you that hydrogen acts like a metal? So HF. It dissociates, but only weakly. Okay? Not very poorly, I should say. Not very well. Whereas HCl dissociates very well. So this would be a weak electrolyte. This is a strong electrolyte. We'll also use the same kind of measure for when we talk about acids and bases. A strong acid dissociates completely. A weak acid only dissociates partially. Okay, so that's all we're looking at. Oh, by the way, if we want to show that it doesn't completely dissociate, you're going to start to see some double arrows like this. What that means is that some of it dissociates, but then some of it pushes back the other way and reforms this HF. So this double arrow is going to show that it goes both directions and is probably a weak electrolyte or a weak acid, as we'll refer to later on. Okay? All right, that concludes 13.1. And let's talk a little bit about 13.2. This is kind of a short chapter, and we're going to talk about what are called colligative properties of solutions. We're still talking about solutions. Remember, we're still talking about, in this case, we're really talking about solids, ions, ionic compounds, and molecular compounds, solids dissolved in water. Okay? Dissolved in water. So all we mean by colligative properties, here's your first point here, you need to know what a colligative property is, are properties that depend on the concentration of solute particles. But it doesn't matter what it is. Okay? So colligative properties are going to be properties of that solution, and it depends on how much is dissolved. What is the concentration? Remember we talked about molarity. Concentration is measured in molarity, and molality. Okay? And mostly we're going to talk about how they change with molality. We're going to use molality a lot in this one. Okay? So molality is going to be, remember, it is the amount of solute, the moles of solute. Here it is right here. Molality is the moles of solute over kilograms of solvent. Moles of solute over kilograms of solvent. Okay? Now, one thing that we want to understand, we're going to be talking about mostly solutions that don't evaporate very well. Those are called non-volatile substances. Okay, so they don't evaporate really easily. We're talking about solutions like that. Okay, and lowering the vapor pressure, that's the pressure above the liquid, depends on non-electrolyte solute concentration. We'll talk more about that probably later on, but the idea here is when a non-volatile substance is dissolved in a solvent. Non-volatile means it doesn't evaporate very easily. Okay, non-volatile substance is dissolved in a solvent, the boiling point of the solvent increases. So when you put salt or sugar into your water, you have to get it to a higher temperature in order for it to boil. Okay? A volume of an aqueous solution contains fewer water molecules than the same volume of pure water. What do I mean by that? Fewer molecules must exist in the gas phase, okay, for the process of evaporation and condensation to balance. So basically what we're saying here is, if you look up here, this is pure water. Pure water is going to have some of the water molecules evaporating, but some of them will be condensing. Okay? You're going to reach a point where, right here, the number of gas particles is going to reach a point where you're going to have the same number of gas particles turn into liquid as you have liquid turning into vapor. Okay? But here, when you put in some type of solute, let's say these are sugar crystals here, okay? Well, you're going to have water that is going to be attracted to that sugar. It's going to be surrounded by it. Therefore, you're going to have fewer water molecules that are free to evaporate, and therefore the vapor pressure up here is going to be less. You're going to have fewer gas particles. Okay? That's one of the things. This is what we're talking about colligative. This is an example. Colligative properties, one of them is going to be boiling point, because boiling point depends on the vapor pressure above the liquid. Okay? So you can see when you add something, a solute, to this water, that solute is going to affect how this water behaves. You're going to have fewer particles evaporating. Well, that's going to affect some of its properties then. Okay? That's what we mean by colligative properties. So let's look at some of these colligative properties. Let's just jump down here to what they are. Here's the first one. The freezing point. The freezing point, that is going to be affected by the concentration of something dissolved in that water. Okay? So we say the freezing point depression, meaning how much the freezing point goes down, is directly proportional to the molal concentration of the solution, meaning molal means how much have you dissolved into that solution, how much salt or sugar have you dissolved. Okay? Now, this should make sense to you. During the wintertime, salt or maybe some other type of mineral is often spread on roads. Why is that? Because when you add salt and water, that salt is going to lower the freezing point of that water. A salt solution has a lower freezing point than pure water. Salt water has a lower freezing point than pure water. So it has to get much, much colder in order for salt water to freeze. So we put salt on the roads so that those roads will have kind of a salt solution covering them, and that will be less likely to freeze than if it was just pure water. Okay? So let's walk through this here. Here's the first point. You need to write this down. Okay, the first one, as I mentioned, is the freezing point is affected by the concentration. We say the freezing point depression. We're going to write that as delta T sub F. Delta T sub F means what? Difference. The difference is your delta. The freezing point, the temperature T of the freezing point, F sub F. Okay? So that's the difference between the pure water and when you have a solution, when you put salt in it or sugar, something like that. Okay? And what does it depend on? Remember, all of these colligative properties depend on what? Concentration. Concentration. So that is molal, small m right here. Okay? And this K right here is just a constant so that you can equate the two sides. So it's a real simple formula. It's a very simple formula. All we say is the amount that the freezing point goes down by, that's delta T right here, is dependent or is equal to this constant, and every solvent is going to have its own constant, times the molal, the concentration of the solute that you have in there. Okay? So just three things. This constant will always be given to you. The molal we can find because it's the number of moles of the solute over the kilograms of the solvent, and that's going to tell us how much the freezing point has gone down by. Okay? These different constants will be given to you, as I mentioned. Okay? So you'll see here, let's take water. Okay? Water normally freezes at 0 degrees Celsius. That's the normal freezing point. And this is the K value for water. Okay? So you can refer to this table in order to get the normal freezing point and also the K value. This delta T is not giving you the new freezing point, it's telling you how much it goes down by. So you have to subtract this value from the normal freezing point for water, which is 0. Let's look at an example here. Okay? So let's say that the actual freezing point of water what is the actual freezing point of water in a solution of 17.1 grams of sucrose in 200 grams of water? Now, the normal freezing point for water is 0 degrees Celsius. We want to know how much is it going to go down by if you add 17.1 grams of sugar into the 200 grams of water. It's real simple. Here's your formula. You'll always have the formula, don't worry. That's it. This M here is molal. Molal is simply what? Let's look at it right down here. It is the amount of solute in moles divided by the mass of the water in kilograms. So we have to find out how many moles of sugar do we have. Well, we are told that we have 17.1 grams. That's not moles. Okay? So we have to take the 17.1 grams and divide by the molar mass of sugar. Well, sugar has 12 carbon atoms, 22 hydrogen. I'm getting these numbers straight from the periodic table. 11 oxygen from the periodic table, 16. All adds up to 342. So you take 17.1 divided by 342. 342 is the mass of 1 mole of sucrose. We don't have 342, we only have 17. So we only have 17 divided by 342 is 0.05 moles of sugar. That is going to go in your numerator right here. And then the mass of the solvent, but the mass is given to you in grams. So you have to divide by 1,000 to change that into kilograms. 200 divided by 1,000 is 0.2. You take 0.05 divided by 0.2, you have the molal. This is the concentration. Concentration of your solution, the concentration of sugar in your solution. That is your M. That is your M in this formula right there. The K value is a constant. You just get it straight from the table that was above. That K value never changes for the freezing point depression constant. It is negative 1.86. Why is it negative? Because adding the sugar forces the freezing point to go down. Okay? Here's your molal from the previous calculation, and we take this constant times the molal, and we get negative 0.465. So what does that mean? It means that the freezing point now of water is 0 minus 0.465. It went down 0.465 degrees. Okay? So this answer right here is a result of 0 minus the 0.465. And of course, you're going to get negative 0.465. Okay? That is the new freezing point of water. But you had to take the original freezing point and add, or in this kind of subtract, the depression. Okay? All right, I'll do some more examples in the review questions. Okay? I would encourage you to look at these examples, by the way. Even though I'm going through these, you could easily go through this sample problem right here and follow it on your own. Make sure you understand it. Okay? Okay, the other colligative property that I want to talk about, the second one here, is boiling point. All right, boiling point. Boiling point simply means that it's going to cause the boiling point to go up. As I mentioned before, if you add salt or some other solute to your water, it's going to boil at a higher temperature. It's going to boil at a higher temperature. Okay, so you're going to increase the boiling point. The freezing point goes down, the boiling point goes up when you add a solute. All right, so this is called boiling point elevation. Boiling point elevation. And you'll notice the formula is very similar. Here's the change in temperature. Sub B is for boiling. You're going to have a K sub B, that's the constant for the boiling point elevation for whatever solvent we're talking about. And it's still molal. It's still talking about molal. Okay, that is the measurement of concentration that we're going to use there. So again, if you'll see here, now we've added boiling point in addition to the freezing here. So for water, water is a very common one. It normally freezes at 0, but if you add a salt or sugar or something else to it, it's going to cause the freezing point to go down, and there's the K value. Notice it's negative. So that K value times whatever the concentration is will give you the amount that the freezing point goes down. The normal boiling point of water is 100 degrees Celsius. Notice the K value is positive. So now when you take this K value, 0.51, times the concentration in molal, it's going to cause the change to go up. It's going to be an increase, and you'll add it to 100. Okay? Let's look at an example. We want to know what is the boiling point. You're going to have 20.1 grams of some solute. It doesn't even matter what it is. Sugar, salt, whatever. Okay? And 400 grams of water. And we are told that the molar mass of this solute, whatever it is, they're giving it to you, 62. Okay? So here's what's given, and we want to find the boiling point elevation. All right? So we're going to we first have to find our moles. Because remember, molality in our formula right here, this molality right there is moles per kilogram of solvent. So we got to find moles. You're not given moles, you're given grams. So you have to take 20.1 grams and divide by its molar mass. This is how many moles of that solute we have. And that goes in the numerator. Then we are told that we have 400 grams of water, but you've got to divide that by 1,000 in order to get kilograms. So that's 0.4000, okay? So when you calculate this right here, you get 0.81 is your molality. That's your molality, and that's going into the formula. Along with this K value, that constant is always 0.51 for water. For water. We multiply them together, and we get 0.41. This is not the new boiling point. That's the increase in the boiling point. Okay? So now, the boiling point of water normally is 100, but now since we added this solute, it went up by 0.41. Now the new boiling point is 100.41, and that is due to the solute that you added. That is a colligative property. Boiling point is a colligative property. The more we add, the higher the boiling point will go. Okay? Again, you can look at that sample problem there, okay, and see if you can figure it out. They pretty much set it up for you. All right, last one. Last one is called osmotic pressure. Osmotic pressure is determined by the concentration of dissolved solid particles as well. Let's talk about what osmotic pressure is. Basically, particles can pass through what is called a semi-permeable membrane. Okay? A semi-permeable membrane basically allows the passage of some particles but blocks the passage of others. Some particles can pass through because they're small enough, others are too big and they won't be able to pass through. That's called a semi-permeable membrane. Okay? So osmotic pressure is related to what is called osmosis. Osmosis is the passing of some particles through a semi-permeable membrane. Okay? So the movement of solvent through a semi-permeable membrane from one side to the other side. It's always going to go from the side of lower concentration to higher concentration. From lower concentration to higher concentration. Okay? Is called osmosis. All right? And that pressure, the osmotic pressure, is the external pressure to stop this osmosis. Let me just show you what I mean here. Okay? So, right here we have a U-tube, a tube here, a U-tube, right? A tube here in the shape of a U, all right? Not the YouTube for videos. It's a tube in the shape of a U here. And there is a semi-permeable membrane right here in between. All right? On one side of this U-shaped tube, we have sugar added to the water. So these are big sugar particles right in here. Okay? Big sugar particles. And on the other side, we have pure water. Okay? Now, what's going to happen? Remember, these water molecules are surrounding the sugar. So you have to imagine that some of these water particles are attracted to the sugar and are surrounding it. Okay? Over here, the water is just free. It's not surrounding or attached to anything. So everywhere there's a sugar molecule, you have water that is attracted to it and wrapped around it and holding on to it. That means you have fewer free water molecules. There's only a few there. Okay? Well, what's going to happen? The sugar particles are too big to pass through. They will not get through the semi-permeable membrane, but water can. So over here, what the water observes, if it can observe, is it has fewer free water on this side over here because lots of them are attracted to the sugar. They're attached to the sugar. Over here we have lots of free water. And so what's going to happen is water is going to push in this direction to try to balance the concentration of free water molecules. There are lots of free water molecules here. There are not very many free water molecules here because so many of them are surrounding and attached to the sugar molecule to dissolve it. And so it wants to balance that. It wants to have equal numbers of free water molecules. It wants to equal that out. So there's going to be a push for water molecules to go to the side that has a higher concentration of sugar to try to dilute it to make it more balanced. Okay? So you will actually see the solution level over on this side actually go up, and this water level will go down because there's more water that is passing from right to left to try to balance out, to help out these water molecules over here that have all the sugar. They need help to dissolve that sugar. So more water is going to come over in order to help dilute this concentrated sugar solution on the left side. Okay? That's osmosis. And the pressure in order to stop that flow, if you were to apply a pressure to push this level back down, that's osmotic pressure. Okay, trying to push it back down. So, guess what? There is a formula for this as well, and it's pretty straightforward. Okay? So the idea is, again, the molality, the concentration, is going to affect the osmotic pressure. Okay, it's going to affect it. All right, let's see here. I guess there's not a formula for the osmotic pressure. It's just a concept that we want to understand here. Okay, so we don't have to worry about a formula for this one here. You just have to understand that water molecules are going to try to come from, this is low concentration of sugar to high. These water molecules are coming over here to help their friends. Think about that way. These water molecules are coming over here to help their water friends, to help dissolve all the sugar over here. They need help, so they're coming over. Okay, reinforcements are coming. They pass through the semi-permeable membrane. Okay? All right, so in summary, the molality, this is concentration. The concentration of dissolved particles is going to affect these colligative properties. What are they? Boiling point, freezing point, and osmotic pressure. Okay? All right. Now, one other little note here. The molality is affected if you've got more particles. Okay? So let me just show you something really quickly here. If you have sugar, when it dissolves, sugar dissolves into individual molecules. But when you have an ionic compound, like sodium chloride, when it dissolves, it breaks apart into two particles. So here you get one sugar, it still remains as one sugar when it dissolves. But sodium, one sodium chloride unit, breaks apart into two particles on the other side. And here you'll notice that one calcium chloride, there's a calcium and chloride, CaCl2, there are actually three particles in there that will all break apart to give you three particles on that side. Okay? So there's one other little trick that we have to apply if we have ionic compounds. All right? So remember our formula? Delta TF equals Km, or delta TB equals Km. This is for freezing and boiling. If it's ionic, we are going to multiply by how many ions are created. So I'm going to put a little I right here, this little I. And this I stands for the number of ions if it's ionic. So if you have 2 ions created, then you have to put a 2 in there for I, because the molality actually doubled. If it creates 3 ions, then you have to put a 3 in there for I, because the molality is actually tripled. Okay? Just for ionic compounds. So that's what happens right here, ladies and gentlemen. Everything is the same. This is 62.5 grams of barium nitrate. This is an ionic compound. Metal, nonmetal. Notice 1 barium, and then the nitrate, you have 2 of those. This is going to break apart into 3 ions. 3 ions. All right, so you'll notice down here, we are going to find the moles of barium nitrate. We're going to take the 62.5 grams, which is given to us right here, 62.5 grams, and we're going to divide by the molar mass. This is the calculation of the molar mass right here. There's barium, and then we have 2 nitrogens and 6 oxygens for a total of 261.35. 62.5 divided by 261.35 gives us 0.239. That's how many moles of barium nitrate we have. That is going into our formula right here. Okay? That's going into the formula. But notice what we did with this 0.239. 0.239, we tripled it. Why? Because for every 1 barium nitrate unit, it is breaking apart into 3, 1, 2, 3 ions. So actually the concentration is tripled. That's why we're multiplying by 3 right there. It gets tripled. That is the number that's going in for the molality. Okay? And then the K value is still a constant, and there is the K times the molality is negative 1.33. So the freezing point went down, that's the change, it went down 1.33 degrees. Okay, so the 0, this is for water, 0 minus 1.33, the new freezing point would be a negative 1.33 degrees Celsius. But you have to be aware, if this is an ionic compound, that you have to multiply by the number of ions that are created in the solution when that ion dissociates, when the ionic compound dissociates. Okay? So that's why I write the formula as delta TF I and then Km. So this I is the number of ions. In this case it was 3. 3 is going there for I. Okay? Okay, these are just some other values. And that concludes 13.2, ladies and gentlemen. All right? And that's all there is for this chapter, just those two sections, 13.1, and talked about ionic compounds dissolving and creating ions and net ionic equation, and then 13.2 talked about the 3 colligative properties: boiling point, freezing point, and osmotic pressure. Okay? All right, I will make up a video that shows the review questions to help you understand those as well. Keep up the good work.